What if I told you that the most destructive force in the universe could also become the most powerful engine ever conceived by the human mind? What if the very object we fear most, the black hole, the cosmic void that devours everything including light itself, could one day be harnessed, caged, wrapped in a shell of human engineering so vast and so audacious that it would make every achievement in the history of civilization look like a child stacking wooden blocks? What if we built a Dyson sphere around a black hole? Pause for a moment and really let that sink in. Not a Dyson sphere around a star. Not around our sun, which is already 93 million miles away and burns at 27 million degrees Fahrenheit at its core. Around a black hole. Around something so gravitationally extreme that space itself bends into a spiral at its edges. Around something that has no surface, no light, no mercy. Just an infinite, invisible hunger pulling everything toward a point of no return. This is not a fantasy. This is not science fiction written in the margins of a pulp novel from the 1950s. This is a question that serious physicists, astrophysicists, and futurists are asking right now. It is a question being explored in peer-reviewed academic journals. It is a question that forces us to confront not just what we know about the universe, but what we believe about our own potential as a species. And the answers, the real, scientifically grounded answers, are more astonishing, more terrifying, and more beautiful than anything you might expect. So ask yourself this right now, sitting wherever you are. If you could build something large enough to contain a black hole, a structure that could capture its energy, its radiation, its very nature, what would you do with that power? And more importantly, what would that power do to you? We are going to explore every dimension of this idea together. We are going to start at the very beginning, at the birth of black holes themselves and the strange physics that governs them. We are going to trace the history of the Dyson sphere concept, understand where it came from, why it matters, and how it evolved from a single brilliant mind's thought experiment into a cornerstone of how we search for intelligent life in the cosmos. Then we are going to do something remarkable. We are going to actually build this thing, step by step, material by material, engineering challenge by engineering challenge, in our minds, guided by real science. We are going to explore what happens when you combine these two ideas, and what the resulting structure could actually do for a civilization like ours, or like any civilization anywhere in the galaxy. And along the way, we are going to encounter mysteries that remain unsolved, paradoxes that make physicists lose sleep, and implications that reach so far into the future that they blur the line between science and philosophy. This story is about energy, ambition, survival, and the fundamental question of whether the universe is something that happens to us, or something we can happen to. Let us begin at the edge of everything we know. To understand why someone would want to build a Dyson sphere around a black hole, you first have to understand what a black hole actually is. Not the Hollywood version, not the glowing, swirling drain of special effects, but the real thing. Because the real thing is stranger and more wondrous than any movie has ever captured. A black hole is a region of space where gravity has become so extreme that nothing, not matter, not energy, not electromagnetic radiation, not light, can escape from it once it has crossed a certain boundary. That boundary is called the event horizon. It is not a physical wall. You cannot touch it, see it, or feel it as you cross it. It is simply the point of no return. The moment you cross the event horizon of a black hole, you are, by the laws of physics as we understand them, gone from the observable universe forever. You will never come back. You will never send a signal back. You will simply fall deeper and deeper into the gravitational well until you reach a point of infinite density called the singularity, where our current understanding of physics completely breaks down. The word singularity is important. It is not just a dramatic term. It is a mathematical term that physicists use to describe a point where equations produce infinite values, values that real physical reality cannot accommodate. When your equations produce an infinity, it usually means one of two things. Either something extraordinary is actually happening, or your theory is incomplete. In the case of black holes, many physicists suspect it is a bit of both. There are several types of black holes, and they differ enormously in size, behavior, and origin. Stellar mass black holes form when massive stars at least 20 to 25 times the mass of our Sun, exhaust their nuclear fuel and collapse under their own gravity. The collapse triggers a catastrophic explosion called a supernova, and if the core that remains after the explosion is heavy enough, gravity wins completely. The core collapses into a black hole. These stellar mass black holes typically have masses ranging from about 3 to several dozen times the mass of our Sun, but they can be as small as a city in terms of the Schwarzschild radius, the radius of the event horizon. Then there are intermediate mass black holes, objects with masses between 100 and 100,000 solar masses, which are more mysterious and harder to observe. We are still learning where they come from and how they form. And then there are the true giants, supermassive black holes. These behemoths lurk at the centers of virtually every large galaxy we have ever observed, including our own Milky Way. The one at the center of the Milky Way is called Sagittarius A star, and it contains about 4 million times the mass of our Sun. 4 million solar masses compressed into a region of space not much larger than our solar system. But even Sagittarius A star is not exceptional by cosmic standards. The black hole at the center of the galaxy M87, the one that was famously photographed in 2019 by the Event Horizon Telescope collaboration, contains about 6.5 billion solar masses. 6.5 billion. The event horizon of that black hole is larger than our entire solar system. How do black holes grow so large? That question itself is one of the most active areas of debate in modern astrophysics. One leading theory suggests that supermassive black holes were seeded in the early universe, possibly from direct collapses of massive gas clouds before stars even formed. Another theory proposes they grew through billions of years of steady feeding, accumulating gas, dust, stars, and even smaller black holes. Likely, the answer involves elements of both, and the truth may be stranger than either theory currently captures. But here's the thing about black holes that is easy to forget in all the drama and fear they inspire. They are not just destroyers. They are also, in a very real sense, some of the most energetically rich objects in the known universe. And to understand why, you need to understand what happens at the boundary between a black hole and everything around it. When material falls toward a black hole, it does not fall straight in, at least not usually. Angular momentum, the same physics that makes a figure skater spin faster when they pull in their arms, causes the infalling material to orbit the black hole before it crosses the event horizon. This orbital material forms a disk, an accretion disk, a swirling, superheated structure of gas and plasma that can reach temperatures of millions of degrees and glow with the luminosity of billions of stars. Quasars, the most luminous persistent objects in the universe, are black holes in the process of consuming enormous amounts of material, and their accretion disks release more energy than any other process we know of in the cosmos. And that energy is real, measurable, and enormous. The efficiency with which a black hole's accretion disk converts mass into energy can reach up to 42% for a maximally rotating black hole, what physicists call a Kerr black hole. Compare that to nuclear fusion, which powers our Sun and every star in the sky, and which converts only about 0.7% of mass into energy. A black hole accretion disk is potentially 60 times more efficient than nuclear fusion as an energy source. 60 times more efficient than the process that lights the stars. Let that number live in your mind for a moment. 60 times more efficient. If you wanted to build a power source for civilization, and you could choose between a star and a black hole, the physics would tell you to choose the black hole every time. But wait, there is more. There is something else about black holes that makes them even more remarkable as potential energy sources, something discovered by a physicist named Stephen Hawking in 1974, and it is perhaps the most mind-bending idea we will encounter in this entire exploration. Hawking's discovery was this: black holes are not perfectly black. They glow. They radiate. At the quantum level. At the level where the strange, probabilistic rules of quantum mechanics operate, the event horizon of a black hole is not a perfectly smooth, silent boundary. Instead, according to quantum mechanics, pairs of particles are constantly popping into existence everywhere in space. This is not science fiction. It is a real, experimentally verified phenomenon called vacuum fluctuation, a consequence of Heisenberg's uncertainty principle. Normally, these particle-antiparticle pairs appear and then annihilate each other almost immediately, leaving no trace. But near the event horizon of a black hole, something different can happen. One particle of the pair can fall into the black hole while the other escapes. From the perspective of an outside observer, the black hole has just emitted a real particle. It has radiated energy. And where does that energy come from? It comes from the black hole's own mass. Over astronomical timescales, a black hole loses mass through this process. It evaporates. This is called Hawking radiation. Now, for large black holes, the stellar mass and supermassive black holes we actually know about, the Hawking radiation is fantastically small and cold. A stellar mass black hole radiates at a temperature of about 60 nanokelvins, which is a billionth of a degree above absolute zero. The cosmic microwave background radiation that fills all of space is about 2.7 kelvins, warmer than a stellar mass black hole's Hawking radiation by a factor of about 45 million. So large black holes are actually absorbing more radiation from the universe than they emit, which means they are growing, not shrinking. But here is the crucial insight. Smaller black holes are hotter. The relationship between black hole mass and Hawking temperature is an inverse relationship. As a black hole loses mass and gets smaller, its temperature rises. A black hole with a mass of a mountain, something about the size of Everest compressed into a subatomic point, would glow at billions of degrees and would be radiating energy ferociously. A microscopic black hole could potentially be an extraordinarily intense energy source, outputting gamma rays in enormous quantities. And this is where the idea of a Dyson sphere around a black hole starts to become not just plausible but tantalizing. Before we go further into the engineering, though, we need to understand where the concept of a Dyson sphere came from, because its history is as fascinating as its physics, and it tells us something profound about the way human imagination works at its most ambitious. The year was 1960. The Cold War was at its height. The space race between the United States and the Soviet Union was accelerating, powered by dreams and fears in roughly equal measure. Sputnik had been launched just 3 years earlier. The world was beginning to genuinely grapple with the idea that humanity's future might extend beyond the Earth. Into this context stepped a man named Freeman Dyson. Freeman Dyson was, to put it plainly, one of the most extraordinary minds of the 20th century. Born in England in 1923, he demonstrated mathematical gifts so extraordinary from such a young age that his trajectory toward the highest levels of theoretical physics was practically inevitable. He made foundational contributions to quantum electrodynamics, the theory describing how light and matter interact, and worked alongside figures like Richard Feynman and Julian Schwinger. He was the kind of physicist who could walk into any area of science and immediately identify the deepest questions. In 1960, Dyson published a short but electrifying paper in the journal Science titled "Search for Artificial Stellar Sources of Infrared Radiation." The paper was only a few paragraphs long, but it contained an idea that has never stopped reverberating through physics, astronomy, and philosophy. Dyson's argument went like this: any sufficiently advanced technological civilization must eventually need more energy than its home planet's surface can provide. The natural solution, the one that physics and astronomy make available to any intelligent species, is to dismantle its solar system's planets and other material and use it to construct a shell around its parent star, capturing all of the star's energy output. Such a shell would make the civilization essentially energy unlimited by stellar standards. Dyson pointed out that from the outside, such a structure would be nearly invisible in optical wavelengths. It would have absorbed all the visible light, but it would glow in the infrared, because all that captured energy would eventually be re-radiated as waste heat. He proposed that astronomers searching for intelligent extraterrestrial life should look not for radio signals, but for unusual infrared sources. Stars that seem to be surrounded by infrared-emitting shells of material at roughly room temperature. The idea ignited the imagination of the scientific community and the public alike. It was the kind of idea that felt immediately, intuitively correct even if the engineering seemed impossibly distant. Of course, an advanced civilization would do this. Of course, if you want more energy and you have a star sitting right there, you would eventually build something to capture it. The logic was almost inescapable. Dyson himself was careful to note that he was not proposing a solid shell. He knew a solid shell around a star would be physically unstable, as it would not be gravitationally bound to the star and would drift in any direction at the slightest perturbation. What he was imagining was more like a swarm of individual objects, perhaps millions of solar-collecting satellites or habitats, spread across the orbital distance of a planet from the star. This is sometimes called a Dyson swarm to distinguish it from the solid shell conception, and it is arguably more physically realistic, though both ideas have been deeply explored in the decades since. But the solid shell version, the one that most people mean when they say Dyson sphere, captured the popular imagination far more powerfully. The idea of a sphere, a perfect enclosed structure surrounding an entire star, is so geometrically clean, so visually overwhelming, so architecturally ambitious that it took on a life of its own in science fiction, in philosophy, and eventually in serious scientific speculation. And that is the version we're going to think about today, with one enormous modification. Instead of building it around a star, we're going to build it around a black hole. Before we start laying the hypothetical foundations of our hypothetical megastructure, let us ask a simple question. Why would anyone want to build a Dyson sphere around a black hole rather than a star? What is the advantage? Because at first glance, it seems counterintuitive. Stars are bright. They pour light and energy into space in every direction. A black hole, by its very definition, traps light rather than emitting it. Why would you want to build a sphere around something that seems to give you nothing? The answer, as we have already begun to see, is that black holes are not really dark at all. They are dark in optical light, yes, but they are surrounded by processes of extraordinary energy output. An actively feeding black hole, one with a healthy accretion disk, is radiating more energy than virtually any other object in the universe. And even a dormant black hole has potential. Through Hawking radiation, through gravitational energy extraction techniques, through mechanisms we will explore shortly, a black hole can be a fantastically productive power source. But there is another reason, one that goes beyond raw energy output, and it has to do with something called the Penrose process. In 1969, the brilliant British physicist Roger Penrose, who would eventually share the Nobel Prize in Physics in 2020 for his work on black holes, described a mechanism by which energy could be extracted from a rotating black hole. This mechanism is now called the Penrose process, and understanding it requires understanding a strange region around rotating black holes called the ergosphere. A rotating black hole, which astrophysicists call a Kerr black hole, after Roy Kerr, who first solved Einstein's equations for a rotating black hole in 1963, does something astonishing to the space around it. It drags space itself along with its rotation. This effect is called frame dragging, and it has been measured experimentally around Earth using the gravity probe B satellite, though on an incomparably smaller scale than around a black hole. Near a rotating black hole, the dragging of space becomes so extreme that within a certain region outside the event horizon, it becomes literally impossible for anything to remain stationary. Everything must move in the direction of the black hole's rotation. This region is called the ergosphere. Now here is what makes the ergosphere extraordinary. It is outside the event horizon. Things can enter the ergosphere and still escape. They are not trapped. And because of the weird physics of the ergosphere, it is theoretically possible to extract energy from it. If you throw a particle into the ergosphere and arrange for it to split into two particles inside the ergosphere, one of which falls into the black hole and one of which escapes, it is possible for the escaping particle to carry away more energy than the particle you threw in. Where does the extra energy come from? It comes from the rotational kinetic energy of the black hole itself. The black hole slows its spin slightly, and that energy is transferred to the escaping particle. This sounds like getting something for nothing, but it is not. You are genuinely extracting the rotational kinetic energy of the black hole, just as you would extract kinetic energy from any spinning object by applying a braking force. The black hole is simply a spinning object on the most extreme scale imaginable, and the Penrose process is a way to tap its kinetic energy. How much energy is available this way? For a maximally rotating Kerr black hole, the total rotational energy that can in principle be extracted is about 29% of the black hole's total mass energy. And mass energy, as Einstein's famous equation E equals mc squared tells us, is an extraordinarily large quantity. For a black hole with a mass of, say, 10 suns, about 20 times 10 to the 30th kilograms, 29% of the mass energy is on the order of 5 times 10 to the 47 joules. That is a number so large it almost defeats description. The total energy output of our Sun over its entire 10 billion year lifetime is about 1.2 times 10 to the 44 joules. A single 10 solar mass rotating black hole contains, in extractable rotational energy alone, roughly 10,000 times the lifetime energy output of our Sun. 10,000 times the lifetime of the Sun in one black hole. This is why the idea of building an energy harvesting structure around a black hole is not just imaginative. It is, from a purely energetic standpoint, the most rational long-term energy strategy available to any civilization that has access to a black hole. And just to be clear, there are black holes everywhere. Our galaxy alone contains an estimated 100 million stellar mass black holes, scattered throughout its spiral arms. The Milky Way's galactic center hosts Sagittarius A star, the 4 million solar mass supermassive black hole we mentioned earlier. Beyond our galaxy, in the observable universe, there are estimated to be 40 quintillion, 40 times 10 to the 18th power, black holes. 40 quintillion. If even a tiny fraction of these are associated with technologically capable civilizations, the universe could be filled with Dyson spheres around black holes. And if that is true, the implications for how we search for intelligent life, and for whether we have already been looking in the wrong places, are staggering. But let us not get ahead of ourselves. Let us start building. Imagine you are an engineer. Not a human engineer of today with our current technology, but an engineer of a civilization perhaps a few thousand years more advanced than ours. A civilization that has colonized its solar system, mastered material science at the nanoscale, harnessed fusion power for propulsion, and begun to think seriously about the deep cosmic future. This civilization has decided to build a Dyson sphere around a black hole. Where do you begin? The first question is, which black hole? This turns out to be an extraordinarily important engineering choice with enormous consequences for every subsequent decision. A small black hole and a large black hole present completely different challenges and opportunities, and the choice between them will shape everything about the resulting structure. Let us consider two extreme cases to bracket the problem. On one end of the scale, consider a primordial black hole with a mass of a large asteroid, say, about 10 to the 20 kilograms. Such a black hole would have a Schwarzschild radius of about 100 femtometers, roughly the size of an atomic nucleus, and would glow at a Hawking temperature of about 10 to the 14th kelvins, which is hotter than the center of a nuclear bomb. It would be radiating energy furiously, emitting gamma rays at a prodigious rate. The total power output from Hawking radiation alone would be about 1.4 times 10 to the 22 watts, comparable to the combined output of a billion stars. But it would also be evaporating rapidly. At that mass, it would have a lifespan of only a few billion years. And controlling something that small, that hot, and that volatile would be engineering of a virtually incomprehensible difficulty. On the other end of the scale, consider a stellar mass black hole of 10 solar masses. Its Hawking radiation is at 60 nanokelvins, negligibly cold, and its Hawking luminosity is about 6 times 10 to the minus 28 watts. You could not power a single LED light with the Hawking radiation from a 10 solar mass black hole. But this black hole is stable on timescales vastly exceeding the current age of the universe, and its accretion disk, if it were actively feeding on infalling matter, could produce luminosities of billions of watts. For a civilization building a Dyson sphere, The ideal target depends on what they want to do. If they want long-term stable power from Hawking radiation, they might prefer a primordial black hole of intermediate mass, massive enough to last for geological timescales but small enough to radiate meaningfully. If they want to harness accretion disk energy, they might prefer a larger black hole and actively feed it material. And if they want to extract rotational energy through the Penrose process, they want a Kerr black hole spinning as fast as physically possible. For our purposes, let us choose a middle path. Let us choose a stellar mass Kerr black hole, a rotating black hole of about 10 solar masses, and let us assume our civilization has figured out how to keep an accretion disk flowing around it by carefully directing infalling material. This gives us a steady, massive energy output from the accretion disk, supplemented by the possibility of Penrose process energy extraction, while the Hawking radiation remains negligible but the black hole remains stable for eons. Now, where is this black hole located? Ideally, it would be in a relatively quiet region of the galaxy, far from other stars and sources of gravitational interference. Stellar mass black holes are typically found in binary systems, paired with another star that provides the infalling material for an X-ray binary, or wandering alone through interstellar space as dark remnants of ancient supernovae. For our structure, we want a relatively isolated black hole, one that our civilization can approach, study, and eventually surround with their megastructure. Now let us think about the Schwarzschild radius of our 10 solar mass black hole. The Schwarzschild radius is the radius of the event horizon, the radius inside which escape is impossible. For a non-rotating black hole, the Schwarzschild radius is given by the formula R equals 2gm divided by c squared, where g is the gravitational constant, m is the mass, and c is the speed of light. For a 10 solar mass black hole, this works out to about 30 kilometers. The event horizon of our black hole is a sphere 30 kilometers in diameter, roughly the size of a small city. But the Dyson sphere would not be placed at the event horizon. It would be placed much further out, far enough that the gravitational forces on the sphere are manageable, and far enough that the sphere can intercept the energy being radiated from the accretion disk. The accretion disk itself might extend from the innermost stable circular orbit, which for a Schwarzschild black hole is at 3 Schwarzschild radii, or 90 kilometers from the center, out to perhaps thousands of Schwarzschild radii. The photon sphere, the radius at which light orbits the black hole, is at 1.5 Schwarzschild radii, or 45 kilometers. The innermost stable circular orbit is where the accretion disk effectively ends, because inside that radius, material spirals inward and falls quickly into the black hole. The energy radiated by the accretion disk spreads outward from this region, and our Dyson sphere needs to be positioned to intercept as much of it as possible. The sphere does not need to be close to the black hole. It just needs to completely surround it. The sphere could be at the distance of, say, 100 Schwarzschild radii, 3,000 kilometers from the black hole, and still capture virtually all the radiated energy, because a complete sphere captures all radiation regardless of its distance from the source, as long as it completely encloses it. Of course, at 3,000 kilometers from a 10 solar mass black hole, the gravitational forces are still substantial. The surface gravity at that distance would be enormous, though not as extreme as at the event horizon. The structural materials of the sphere would need to withstand these gravitational stresses while also withstanding the intense heat and radiation from the accretion disk. And here we arrive at the first truly formidable engineering challenge: materials. What do you build a Dyson sphere out of? This question sounds simple until you start thinking about what the sphere actually needs to withstand. Let us make a list of the challenges our sphere faces. First, heat. The accretion disk of an active black hole radiates at temperatures of millions of degrees, primarily in X-ray and gamma-ray wavelengths. Any material placed close to this source of radiation would absorb enormous amounts of energy and rapidly reach temperatures far beyond any conventional material's melting point. Today's most heat-resistant materials, tungsten carbide, hafnium carbide, titanium diboride, begin to fail at temperatures above a few thousand degrees Celsius. An accretion disk can be 1,000,000 degrees or more. The difference is not marginal. It is astronomical. Second, Radiation. The high-energy radiation from an accretion disk is not just hot, it is physically destructive at the atomic level. X-rays and gamma rays can ionize atoms, break chemical bonds, and cause what material scientists call radiation damage. The displacement of atoms from their lattice positions, the creation of defects and voids, and the gradual embrittlement and failure of structural materials. Even the most radiation-hardened materials available today would degrade relatively quickly under the radiation environment close to an active black hole. Third, tidal forces. In the vicinity of a black hole, the difference in gravitational pull between one side of an object and the other, what physicists call the tidal force, can be powerful enough to tear objects apart. This process is called spaghettification, and it has actually been observed when stars wander too close to supermassive black holes in what astronomers call tidal disruption events. For a sphere at a sufficiently large distance from a stellar mass black hole, the tidal forces would be manageable, but the structure must still be designed to withstand them. Fourth, structural stability. A Dyson sphere around a black hole is not gravitationally stable in the same way a planet's orbit is. The sphere surrounds the black hole, and the net gravitational force on any given section of the sphere from the black hole is balanced by the forces from adjacent sections. But this balance is inherently unstable. Any perturbation, an asymmetric collision, an uneven distribution of mass, even the gravitational pull of a passing star, could cause sections of the sphere to drift. Unlike a planet in orbit, which is maintained in stable orbit by its angular momentum, a shell enclosing a gravitational source has no equivalent stabilizing force. This is actually a serious structural problem that physicists have identified with the classic Dyson sphere concept, and it applies equally or more powerfully to a Dyson sphere around a black hole. So how might an advanced civilization solve these problems? The honest answer, from our current scientific vantage point, is that we do not know in detail. The engineering involved is so far beyond our current capabilities that we can only gesture at the general directions that solutions might take. But we can point to real physical possibilities that current science does not rule out. For the materials problem, one promising direction is the development of metamaterials, engineered materials whose properties are determined not by their chemical composition but by their microstructure. Current research into metamaterials has already produced materials with properties that natural materials cannot provide, including negative refractive indices and near-perfect absorption across broad electromagnetic spectra. Future metamaterials, designed at the nanoscale or even the atomic scale, might achieve heat resistance and radiation hardness far beyond anything we currently possess. Some theorists have even suggested that a sufficiently advanced civilization might be able to engineer materials whose electromagnetic properties are tuned to reflect rather than absorb high-energy radiation, essentially functioning as mirrors for X-rays and gamma rays. For the structural stability problem, one solution that has been proposed is to not build a rigid sphere at all, but rather a swarm of orbiting elements, the Dyson swarm concept Dyson himself originally envisioned. A collection of thousands or millions of individual satellites, each in a stable orbit around the black hole, would collectively intercept most of the radiated energy without requiring any of them to maintain a fixed position relative to the others. The challenge with this approach around a black hole is that the orbits are more complex than around a star, the effects of general relativity are significant, and stable orbital configurations must be carefully chosen. Another approach involves what some have called a Dyson shell with active support. A rigid shell that is kept in place not by passive structural strength but by active forces. This could involve electromagnetic repulsion, carefully controlled rocket engines, or even the radiation pressure of the energy being captured pushing outward against the shell's inward tendency to fall toward the black hole. This kind of active support is energy intensive, but for a structure designed to capture energy, the feedback loop might be self-sustaining. But perhaps the most intriguing material solution comes from a direction so exotic that it borders on fantasy, except that current physics does not forbid it. Strange matter. Strange matter is a hypothetical form of matter composed of roughly equal proportions of up quarks, down quarks, and strange quarks, the fundamental particles from which protons and neutrons are made. Normal matter, the stuff of atoms, stars, and people, contains only up and down quarks. Strange matter, if it exists and is stable, might have extraordinary properties. Extreme density, possibly extreme strength, and possibly unusual electromagnetic properties. The Bodmer-Witten hypothesis in nuclear physics suggests that strange quark matter might actually be the true ground state of matter, meaning that under the right conditions, ordinary matter would spontaneously convert to strange matter and remain stable forever. We have never synthesized strange matter in a laboratory. We do not know for certain that it is stable at macroscopic scales. But if it exists, and if a future civilization could produce and manipulate it, the resulting material might be capable of withstanding conditions that would destroy any ordinary matter. Let us continue building our sphere, moving past the materials question for now, and assuming that our advanced civilization has solved it through some combination of approaches we can currently envision and techniques we cannot yet imagine. The materials question is, after all, not unique to this structure. It is a challenge that advances in material science continuously push the frontier of, and a civilization thousands of years ahead of us in technology would have thousands of years of material science progress beyond our current state. So our sphere is being built. What does the construction process actually look like? The scale of the project is so enormous that ordinary intuitions about construction fail completely. Building a Dyson sphere, even a relatively small one at 100 Schwarzschild radii around a 10 solar mass black hole, which means a radius of 3,000 kilometers, requires materials on a planetary scale. A sphere of radius 3,000 kilometers has a surface area of about 113 million square kilometers, comparable to the surface area of the Earth. If the shell is even a meter thick, the volume of material required is 113 trillion cubic meters. At the density of steel, that is about 880 trillion metric tons of material, roughly 100 times the mass of the Moon. This is an extraordinary amount of material, but it is not an amount that is physically impossible to source. Our solar system contains about 4 times 10 to the 27th kilograms of material in non-solar bodies. Planets, moons, asteroids, comets. That is enough material to build Dyson spheres of this modest size many times over. A civilization that has access to and can dismantle asteroids, comets, and eventually smaller planetary bodies can, over long timescales, accumulate the raw materials needed for this construction project. The construction itself might take place in stages. First, perhaps, mining and processing raw materials from nearby bodies, asteroids, moons, or small planets in whatever system the black hole is associated with or has been brought near to. Then manufacturing, converting raw materials into structural components that can be transported and assembled in the radiation environment around the black hole. Then assembly, positioning each component in its correct location and joining it to its neighbors, all while managing the thermal and radiation challenges of working in close proximity to an active accretion disk. This construction process would need to be at least partially automated. The radiation environment around an active black hole is lethal to biological organisms, and probably to conventional electronics as well. Radiation-hardened robotic systems, or artificial intelligences capable of directing robotic systems autonomously, would be needed for the close-in work. Humans or other biological intelligent beings might direct operations from safe distances, receiving telemetry from their robots and sending commands back at the speed of light. And here is something worth pausing on, because it raises a question that you might find yourself asking even without prompting. What does the construction of a Dyson sphere do to the civilization building it? Not physically, but culturally, philosophically, existentially. What happens to a society that undertakes a project that will take thousands or millions of years to complete? A project so large that no individual who contributes to it will live to see it finished? Does the project become a religion, a government, an identity? Does it unite the civilization, giving it a shared purpose that transcends the petty conflicts of ordinary politics? Or does it fracture the civilization, with different factions arguing about priorities, resource allocation, and the ultimate use of the structure? These questions are not engineering questions, but they may be more important than any of the engineering questions. The history of human civilization contains many examples of societies that attempted multi-generational projects: cathedrals, irrigation systems, road networks, And the social dynamics of those projects shape the societies as much as the projects shape the landscapes. A project the scale of a Dyson sphere would be to those historical examples as a supermassive black hole is to a bowling ball. The social transformation involved would be total. Ask yourself this: what is the largest project you can imagine humanity successfully completing today? The International Space Station took 15 countries and $100 billion in 30 years to build, and it is a structure about the size of a football field. Now scale that up by a factor so enormous it has no name. What does humanity have to become to accomplish something like that? And is that transformation something we should want or something we should fear? Let us now turn to what the completed Dyson sphere around a black hole would actually do, what it would produce, how its energy would be used, and what the experience of living inside or near such a structure might be like. The energy output of our black hole, with its active accretion disk, is somewhere in the range of what astronomers call the Eddington luminosity, the maximum luminosity at which radiation pressure balances gravitational attraction for infalling material, beyond which radiation would push material away and stop the accretion. For a 10 solar mass black hole, the Eddington luminosity is about 1.3 times 10 to the 32 watts, about 30,000 times the luminosity of our Sun. The completed Dyson sphere would intercept all of this energy, virtually every photon and particle of radiation emitted by the accretion disk, and convert it into useful work. What kind of useful work? The possibilities are almost incomprehensible in their scope. The most obvious use is electricity, or whatever form of organized energy the civilization prefers. The sphere could be covered in photovoltaic collectors tuned to absorb the specific wavelengths of radiation produced by the accretion disk. Given that the dominant radiation from an accretion disk is X-rays rather than visible light, these collectors would need to be X-ray sensitive, analogous to but vastly more sophisticated than solar panels. The energy so collected could be stored in superconducting rings or other high-density energy storage systems, or transmitted wirelessly to consuming systems throughout the civilization's domain. Another possible use is propulsion. The energy from a Dyson sphere around a black hole is so vast that it could, in principle, be directed outward as a collimated beam of radiation, essentially the civilization scale laser. Such a beam could be used to push spacecraft to relativistic velocities, allowing interstellar travel on timescales of decades rather than millennia. This is essentially the concept behind proposed laser sail or beam-powered propulsion systems, scaled up by a factor that boggles the mind. A third possible use is computation. Some theorists, most notably physicist and astronomer Michael Lambton and, in a different context, philosopher Nick Bostrom, have argued that the ultimate destiny of an advanced civilization might be computational. The simulation of vast virtual environments and the running of incredibly complex information processing systems. The energy from a Dyson sphere around a black hole could power computation on a scale that would allow the simulation of environments of planetary complexity, or the running of artificial intelligence systems of a sophistication that dwarfs anything we can currently imagine. And then there is a use that is perhaps the most audacious of all: the deliberate manipulation of the black hole itself. And civilization with a Dyson sphere already in place around a black hole has not just captured the black hole's energy, it has surrounded the black hole and can, in principle, control what falls into it and what does not. By carefully managing the accretion disk, controlling the flow rate of infalling material, the composition of that material, and the geometry of its infall, the civilization could in principle adjust the black hole's spin, charge, and mass. They could tune the black hole like an instrument. This is not idle speculation. The physics of black hole accretion is well enough understood to see how, in principle, different modes of material inflow would change the black hole's properties differently. And a black hole of controlled properties is far more useful than an uncontrolled one, because different physical processes are optimal at different combinations of mass and spin. For example, the efficiency of the Penrose process depends on the spin of the black hole. A maximally spinning black hole, one at what physicists call the Kerr limit, allows the most energy to be extracted. By managing the angular momentum of infalling material, a civilization could maintain their black hole at or near the Kerr limit, maximizing their energy return from the Penrose process indefinitely. Now let us turn to something even more fascinating. The possibility of using the Dyson sphere around a black hole as a time machine. Not in the science fiction sense of jumping between arbitrary points in history. That remains deeply speculative and possibly physically impossible. But in a very real, physics-certified sense, time passes differently near a black hole than far from one, and a civilization that lives near, or on, a Dyson sphere around a black hole could exploit this effect in profound ways. This effect is called gravitational time dilation, and it is a direct consequence of Einstein's general theory of relativity. Near a massive object, time passes more slowly than it does in flat space far from any mass. This is not a metaphor or an approximation. It is a precise, measured, experimentally verified effect. GPS satellites have to correct for both special relativistic and general relativistic time dilation effects to maintain their accuracy, because they are in a slightly different gravitational field than the receivers on Earth's surface. The time dilation near a black hole is vastly more extreme. At the innermost stable circular orbit of a non-rotating black hole, 3 Schwarzschild radii from the center, time passes at about 82% of the rate it does far from the black hole. An observer at that location would age at 82% the rate of an observer far away. Closer in, the effect becomes more dramatic. Hover at 2 Schwarzschild radii. The photon sphere is at 1.5 and the event horizon at 1, and time dilation becomes extreme. At the event horizon itself, time dilation becomes infinite. An observer hovering at the event horizon, which is physically impossible, but as a limit, would experience time stopping from the perspective of a distant observer. What does this mean for our Dyson sphere inhabitants? If the sphere is positioned close to the black hole, say, at 10 Schwarzschild radii, which for our 10 solar mass black hole is 300 kilometers from the center, the time dilation factor is significant. Inhabitants on the sphere would age more slowly than inhabitants of other civilizations far from black holes. Over long timescales, this could become an enormous effect. A civilization living on a Dyson sphere close to a black hole might age 1 year for every 10 years of cosmic time, or 1 year for every 1,000, depending on how close to the black hole their structure is. This would give them a profound temporal advantage in certain contexts. They could wait out long cosmic events, survive long periods of scarcity, or effectively fast forward the evolution of the universe from their perspective while aging slowly. But it also creates an unbridgeable communication gap with other civilizations. Messages sent to them would arrive seeming to take a long time, and messages they send to the wider universe would seem to come from the far future. Time dilation near black holes is already a rich subject in scientific discussions about the long-term future of the universe. Some physicists, including Kip Thorne, whose work inspired the film Interstellar, have explored in careful mathematical detail how time dilation near black holes could be used as a kind of natural time capsule or survival mechanism. A civilization that retreated to the vicinity of a black hole could, in effect, skip forward in cosmic time, emerging into a universe billions of years advanced from when they left. But there is a darker side to this picture. A civilization living on a Dyson sphere around a black hole is not living in a comfortable, Earth-like environment. They are living in a region of intense radiation, strong tidal forces, and bizarre gravitational effects. The experience of everyday life near a black hole would be alien in ways that are hard to fully articulate. Consider light. Our human visual system evolved on a planet orbiting a yellow-white dwarf star, bathed in visible light of wavelengths between about 380 and 700 nanometers. The primary radiation from a black hole's accretion disk is in X-rays, with wavelengths orders of magnitude shorter than visible light and energies orders of magnitude higher. There is no visible glow from a black hole, at least not in the dominant emission channel. An observer near our Dyson sphere would not see a brilliant star-like light flooding through the windows of their habitat. They would see, if they could see at all in the conventional sense, something stranger. A disk of roiling, superheated plasma emitting primarily in wavelengths their unaided eyes cannot detect. The visual appearance of the environment near a black hole is itself extraordinary. The extreme curvature of space around the black hole acts as a gravitational lens, bending light from background stars around the black hole and producing an optical effect called the photon ring or the shadow. The black hole's shadow, the absence of light in the region of the event horizon, would appear as a perfect dark circle, surrounded by a bright, distorted ring of light from stars whose light has been bent around the black hole before reaching the observer's eyes. The Event Horizon Telescope image of M87 star that made the news in 2019 showed this structure: a dark shadow surrounded by a bright, asymmetric ring of light. This is what you would see if you looked toward the black hole from your Dyson sphere habitat, through a viewport designed to image in the relevant wavelengths. It would be, by any measure, the most visually extraordinary view available to any being in the universe. Now, one of the most extraordinary questions we can ask about our Dyson sphere around a black hole is this: what would happen if we could make it from the inside? What would it be like to actually live in or on such a structure? The inside of a Dyson sphere surrounding a star, in the conventional conception, would be a vast, enclosed habitat, a surface area millions of times that of Earth, all bathed in the light of the central star, potentially habitable if the gravity and temperature could be managed. But the inside of a Dyson sphere around a black hole is something very different. There is no light pouring inward from the center. There is radiation, intense, dangerous, mostly in X-rays, pouring outward from the accretion disk. The inner surface of the sphere would be the most hostile radiation environment imaginable, requiring either enormously thick shielding or a complete abandonment of the concept of living on the inner surface. More realistically, inhabitants of a Dyson sphere around a black hole would live on the outer surface, or inside the structure itself, shielded from the central radiation by the sphere's own thickness and by additional radiation shielding. They would experience whatever gravity is provided by rotating sections of the sphere, a technique called centrifugal habitation, already discussed extensively in space habitat design, and they would be surrounded not by the open sky of a planet, but by the curved interior of their habitat modules and the endless starfield of the galaxy beyond the sphere. The experience of looking down toward the black hole from the outer surface of the sphere would be different from looking up toward the stars. Below, inward, lies the engine of their civilization, invisible but furiously energetic, an inexhaustible furnace of gravitational and relativistic physics powering everything around them. Above, outward, lies the galaxy, the rest of the universe, slowly evolving, billions of stars in their slow orbits around the galactic center, the faint smear of other galaxies at the edges of the observable cosmos. This is an existence unlike anything a human being has ever experienced. It is an existence defined not by nature, by the weather, the seasons, the rhythms of a planet, but by engineering. Every aspect of the environment would be designed. The temperature, the light levels, the air composition, the radiation shielding, the artificial gravity. Nothing would be left to chance, because nothing could be. This is an existence so thoroughly embedded in technology that the distinction between natural and artificial would have ceased to have any meaning. What does this mean for our Dyson sphere inhabitants? If the sphere is positioned close to the black hole, say, at 10 Schwarzschild radii, which for our 10 solar mass black hole is 300 kilometers from the center, the time dilation factor is significant. Inhabitants on the sphere would age more slowly than inhabitants of other civilizations far from black holes. Over long timescales, this could become an enormous effect. A civilization living on a Dyson sphere close to a black hole might age 1 year for every 10 years of cosmic time, or 1 year for every 1,000, depending on how close to the black hole their structure is. This would give them a profound temporal advantage in certain contexts. They could wait out long cosmic events, survive long periods of scarcity, or effectively fast forward the evolution of the universe from their perspective while aging slowly. But it also creates an unbridgeable communication gap with other civilizations. Messages sent to them would arrive seeming to take a long time, and messages they send to the wider universe would seem to come from the far future. Time dilation near black holes is already a rich subject in scientific discussions about the long-term future of the universe. Some physicists, including Kip Thorne, whose work inspired the film Interstellar, have explored in careful mathematical detail how time dilation near black holes could be used as a kind of natural time capsule or survival mechanism. A civilization that retreated to the vicinity of a black hole could, in effect, skip forward in cosmic time, emerging into a universe billions of years advanced from when they left. But there is a darker side to this picture. A civilization living on a Dyson sphere around a black hole is not living in a comfortable, Earth-like environment. They are living in a region of intense radiation, strong tidal forces, and bizarre gravitational effects. The experience of everyday life near a black hole would be alien in ways that are hard to fully articulate. Consider light. Our human visual system evolved on a planet orbiting a yellow-white dwarf star, bathed in visible light of wavelengths between about 380 and 700 nanometers. The primary radiation from a black hole's accretion disk is in X-rays, with wavelengths orders of magnitude shorter than visible light and energies orders of magnitude higher. There is no visible glow from a black hole, at least not in the dominant emission channel. An observer near our Dyson sphere would not see a brilliant star-like light flooding through the windows of their habitat. They would see, if they could see at all in the conventional sense, something stranger. A disk of roiling, superheated plasma emitting primarily in wavelengths their unaided eyes cannot detect. The visual appearance of the environment near a black hole is itself extraordinary. The extreme curvature of space around the black hole acts as a gravitational lens, bending light from background stars around the black hole and producing an optical effect called the photon ring or the shadow. The black hole's shadow, the absence of light in the region of the event horizon, would appear as a perfect dark circle, surrounded by a bright, distorted ring of light from stars whose light has been bent around the black hole before reaching the observer's eyes. The Event Horizon Telescope image of M87 star that made the news in 2019 showed this structure, a dark shadow surrounded by a bright, asymmetric ring of light. This is what you would see if you looked toward the black hole from your Dyson sphere habitat, through a viewport designed to image in the relevant wavelengths. It would be, by any measure, the most visually extraordinary view available to any being in the universe. Now, one of the most extraordinary questions we can ask about our Dyson sphere around a black hole is this: what would happen if we could make it from the inside? What would it be like to actually live in or on such a structure? The inside of a Dyson sphere surrounding a star, in the conventional conception, would be a vast, enclosed habitat, a surface area millions of times that of Earth, all bathed in the light of the central star, potentially habitable if the gravity and temperature could be managed. But the inside of a Dyson sphere around a black hole is something very different. There is no light pouring inward from the center. There is radiation, intense, dangerous, mostly in X-rays, pouring outward from the accretion disk. The inner surface of the sphere would be the most hostile radiation environment imaginable, requiring either enormously thick shielding or a complete abandonment of the concept of living on the inner surface. More realistically, inhabitants of a Dyson sphere around a black hole would live on the outer surface, or inside the structure itself, shielded from the central radiation by the sphere's own thickness and by additional radiation shielding. They would experience whatever gravity is provided by rotating sections of the sphere, a technique called centrifugal habitation, already discussed extensively in space habitat design, and they would be surrounded not by the open sky of a planet, but by the curved interior of their habitat modules and the endless starfield of the galaxy beyond the sphere. The experience of looking down toward the black hole from the outer surface of the sphere would be different from looking up toward the stars. Below, inward, lies the engine of their civilization, invisible but furiously energetic, an inexhaustible furnace of gravitational and relativistic physics powering everything around them. Above, outward, lies the galaxy, the rest of the universe, slowly evolving, billions of stars in their slow orbits around the galactic center, the faint smear of other galaxies at the edges of the observable cosmos. This is an existence unlike anything a human being has ever experienced. It is an existence defined not by nature, by the weather, the seasons, the rhythms of a planet, but by engineering. Every aspect of the environment would be designed. The temperature, the light levels, the air composition, the radiation shielding, the artificial gravity. Nothing would be left to chance, because nothing could be. This is an existence so thoroughly embedded in technology that the distinction between natural and artificial would have ceased to have any meaning. Subsequent observations have accumulated evidence pointing toward a more prosaic explanation: dust clouds of unusual composition and distribution around the star, possibly from a disintegrated comet or planet. But the episode was remarkable for illustrating how seriously some astronomers take the possibility of detecting megastructures. Tabby's star was a genuine false alarm, or possibly a false alarm. The debate is not entirely closed, but it showed that the universe contains objects that look, at first pass, like they could be megastructures, and that distinguishing megastructures from natural phenomena is a genuine scientific challenge. Now, what about a Dyson sphere around a black hole? The observational signature would be different from one around a star. You would not expect to see a star whose optical light has disappeared. The black hole has no optical light to begin with. Instead, you would expect to see a black hole whose characteristic high-energy radiation, X-rays, gamma rays, has been absorbed and re-radiated at much lower energies, possibly in the infrared or microwave. From Earth, this might look like an X-ray source that is anomalously faint compared to what you would predict from its environment, surrounded by an unusual infrared halo. More specifically, Dyson spheres around black holes would likely have waste heat signatures. All that captured energy must ultimately be re-radiated. Thermodynamics demands it. A civilization using energy to do work will necessarily produce waste heat, which must be radiated away into space. The surface temperature of the Dyson sphere, determined by the balance between energy input from the black hole and energy output as thermal radiation, would produce a characteristic temperature, and that temperature might be detectable with sufficient astronomical instruments. Several researchers, including those associated with the Glimpsing Heat from Alien Technologies Project, sometimes called GHAT, have actually surveyed large databases of infrared observations looking for anomalously bright infrared sources that might indicate the presence of waste heat from Dyson spheres. While no confirmed detections of megastructures have been made, these surveys have placed constraints on what fraction of stars and galaxies in various databases could be harboring advanced technological civilizations, and have flagged a number of interesting candidates for follow-up study. One particularly interesting result from this line of research comes from Roger Griffith and Jason Wright, who in 2015 examined data from the WISE infrared satellite on 50 million galaxies and found a handful of galaxies, about 50, that appeared unusually bright in the mid-infrared compared to what their optical brightness would predict. They categorized these as galaxies with possible alien civilizations, not because they had found alien civilizations, but because these galaxies had properties consistent with what you would expect if a significant fraction of their stars were surrounded by energy-harvesting megastructures. Most of these have likely natural explanations. Starburst galaxies with unusually high star formation rates, dusty active galactic nuclei, and similar phenomena can produce similar signatures. But the act of looking for them is real science, and the framework for thinking about what to look for is well developed. If you were to find a galaxy in which certain black holes showed anomalously dim X-ray emissions surrounded by anomalously bright infrared halos, and if you could rule out natural explanations, that might be the observational signature of a Dyson sphere around a black hole. We do not have the observational sensitivity to make such a detection today. But with next-generation X-ray observatories, the proposed LINX X-ray Observatory, for example, or the Advanced Telescope for High-Energy Astrophysics currently being developed in Europe, the detection threshold might eventually come down to where such signatures could be identified in nearby galaxies. Now we should spend some time with one of the most philosophically challenging implications of building a Dyson sphere around a black hole. What it would mean for our understanding of nature, and what it would reveal about the relationship between intelligence and the cosmos. There is a deep and often unexamined assumption in human culture, and one might speculate, in the cultures of any sufficiently evolved intelligence, that the universe is a backdrop, a stage, a given. Stars shine, planets orbit, black holes devour. These are things that happen, forces and objects that constitute the scenery against which the drama of life and thought plays out. We observe the universe. We study it. We adapt to it. But we do not, in any meaningful sense, change it. A civilization that builds a Dyson sphere around a black hole has made a different choice. They have taken one of the most extreme, most powerful, most fundamental objects in the universe, an object defined by physics at its most absolute, and they have enclosed it, surrounded it, put it to work. They have not adapted to the universe. They have subordinated a portion of it to their needs. They have answered the universe's vast indifference with engineering. This is a kind of hubris that human civilizations have dreamed about but never approached. And it raises a question that haunts all discussions of superintelligent civilizations and megastructures. At what point does a civilization stop being a part of nature and become something else? At what point does intelligence transition from being an evolved feature of a universe that is indifferent to it, to being a force that genuinely shapes the trajectory of the universe itself? Physicist Freeman Dyson, our Dyson sphere Dyson, spent much of his later life thinking about exactly this question. In his remarkable 1979 paper, Time Without End, Physics and Biology in an Open Universe, Dyson argued that an open universe, one that expands forever, as current evidence suggests our universe will, offers essentially unlimited possibilities for the persistence and evolution of intelligence. He showed, using careful thermodynamic arguments, that a sufficiently organized intelligence could, in principle, continue to think and act for an infinite subjective time, even as the universe cools and expands toward heat death, by periodically slowing its metabolism and hibernating between periods of activity. The energy needs for this indefinite operation would decrease over time, and the available energy, from the cooling of black holes via Hawking radiation, from the last remnants of stellar activity, would always be just enough to sustain the enterprise. Dyson was not just speculating about physics. He was making a philosophical argument that the universe is not hostile to intelligence, that physics contains within it the possibility of eternal thought, and that the proper destiny of intelligent beings is to inhabit that possibility rather than succumb to the apparent despair of cosmic cold death. A Dyson sphere around a black hole is a physical embodiment of exactly this Dysonian vision. It is the construction of a machine for surviving the long cosmic future, for extracting every joule of energy from one of the last energy-rich objects in an aging universe and using it to sustain whatever counts as life and thought on timescales the current universe cannot even witness. But there is another perspective, a more sobering one, that we should sit with for a moment. Because for all the wonder of this concept, it comes with risks that are as large as the ambitions. Think about what it means to be a civilization whose existence depends entirely on a single megastructure surrounding a black hole. Your civilization's entire energy supply, every computation, every habitat, every light, every life support system, is powered by this one object. If the sphere fails, if a section collapses, if the accretion disk is disrupted, if a passing star's gravity perturbs the structure beyond its tolerance, the consequences could be civilizational extinction. Not just a power outage. Extinction. This is a profound vulnerability. A civilization that has concentrated all of its existential eggs in one basket, even a basket as magnificent as a Dyson sphere around a black hole, has made itself extraordinarily brittle. And the greater the civilization's dependence on the structure, the greater the catastrophe if the structure fails. History, human history, that is, offers instructive parallels. The ancient Egyptians built their civilization around the Nile, and they were extraordinarily vulnerable to changes in the Nile's flooding patterns. When the floodings changed, as they did during periods of climate shift, Egyptian civilization suffered. Ancient Mesopotamia built elaborate irrigation systems that, when they eventually silted up or were disrupted by political conflict, contributed to the collapse of those civilizations. Every civilization in human history that has concentrated its dependencies too completely on a single system has been eventually punished for that concentration. A civilization with a Dyson sphere around a black hole would need to ask itself, what is our backup plan? What happens if the sphere fails? What other energy sources do we maintain? What other systems do we preserve that could sustain life if the megastructure were lost? These are not just practical engineering questions. They are questions about values, about whether a civilization prioritizes bold transformation or cautious resilience, maximum capability or maximum safety. And here's where the concept of a Dyson sphere around a black hole intersects with something that has become increasingly important in discussions of civilization risk: existential risk management. The study of existential risks, threats that could cause the permanent destruction or permanent crippling of human or civilizational potential, has emerged as a serious academic field, associated with thinkers like Nick Bostrom, Toby Ord, and researchers at institutions like the Future of Humanity Institute and the Center for Human-Compatible AI. One of the key insights of this field is that civilizations at the stage of building megastructures are also civilizations that have introduced new categories of existential risk that did not previously exist. A civilization that has not built a Dyson sphere around a black hole cannot have it fail. But a civilization that has built one has introduced a failure mode so catastrophic and total that it must be designed against with the most extraordinary care. The engineering challenge, then, is not just to build the sphere. It is to build it in a way that is resilient, redundant, and survivable, qualities that are sometimes in tension with raw engineering ambition. Let us now turn to one of the deepest and strangest aspects of black hole physics, something that has been the subject of intense research and debate for decades, and that has profound implications for any civilization interacting closely with a black hole. This is the black hole information paradox. The information paradox is one of the most profound, unresolved problems in theoretical physics. It arises from a conflict between two pillars of modern physics: quantum mechanics and general relativity. Quantum mechanics asserts that information is conserved. This is not a metaphor, it is a precise mathematical statement. In quantum mechanics, the evolution of any physical system is described by a unitary transformation, which means it is reversible. Given the current state of a quantum system, you can calculate both its future and its past states. Information is never truly destroyed. It may become scrambled and inaccessible in practice, but in principle, it can always be recovered. General relativity, on the other hand, describes black holes as perfect sinks. Once something falls past the event horizon, it is gone from the observable universe. The singularity at the center destroys physical structure, and with it, according to classical general relativity, information about what fell in. A kilogram of gold and a kilogram of dust give exactly the same contribution to the black hole's mass, charge, and spin. The three quantities that, according to the no-hair theorem, completely describe a black hole state. All other information about the infalling material, its composition, its structure, its quantum state, is apparently lost. But wait, what about Hawking radiation? When Hawking showed that black holes radiate thermally, he showed that the radiation is truly thermal. It has no correlation with the specifics of what fell into the black hole. A black hole that absorbed only books would radiate identically to a black hole that absorbed only planets. The Hawking radiation carries no memory of the infalling material. If a black hole eventually evaporates completely through Hawking radiation, then all the information about what it absorbed is gone forever. Quantum mechanical unitarity is violated. This is the information paradox, and it is a genuine crisis in theoretical physics. It has been called one of the most important problems in physics because it reveals a deep incompatibility between the two most successful theories we have ever created. One of them must be wrong, or at least incomplete, in the regime where both apply, near black hole event horizons. The debate about the information paradox has generated some of the most creative theoretical physics of the last half-century. Proposals for its resolution have included the black hole complementarity of Leonard Susskind and Gerard T. Hooft, which suggests that information is simultaneously inside and outside the black hole from the perspectives of different observers. The fuzzball proposal from string theory, which replaces the smooth event horizon with a complex quantum structure at the Planck scale. The holographic principle, which suggests that all the information inside a black hole is encoded on its event horizon, in a way analogous to a hologram. And most recently and controversially, the firewall proposal of Ahmed Almhiri and collaborators, which suggests that the event horizon is not the smooth, uneventful region that general relativity predicts, but instead a wall of high-energy radiation that would instantly incinerate anything trying to cross it. In 2019 and 2020, a remarkable development occurred in this debate. Physicists studying the information paradox using techniques from string theory and the AD/CFT correspondence a mathematical duality between a certain type of gravitational theory and a quantum field theory without gravity, derived a result suggesting that information does escape from black holes, encoded in subtle quantum correlations in the Hawking radiation that are only detectable in principle over the entire lifetime of the black hole's evaporation. This result relied on a concept called the island formula, which modifies the calculation of entropy in the presence of quantum gravity effects near the event horizon. This does not fully resolve the paradox. The exact mechanism by which information escapes remains deeply unclear, and the firewall debate continues. But it suggests that quantum mechanics wins. Information is not destroyed by black holes. The information that falls and comes back out, eventually, encoded in the Hawking radiation. The black hole is not a perfect sink after all. What does this mean for a civilization operating a Dyson sphere around a black hole? On one level, it is reassuring. The black hole is not a place of ultimate, irreversible loss. On another level, it raises fascinating practical questions. If information escapes from black holes in the Hawking radiation, and if Hawking radiation can be collected, could a sufficiently advanced civilization read information out of the Hawking radiation of their black hole? Could they, in principle, retrieve information about objects that fell into the black hole billions of years ago? This may sound absurd, but consider, the information is, according to the latest thinking, actually there in the Hawking radiation. Recovering it would require extraordinary computational power and a complete quantum theory of gravity, both of which our hypothetical civilization presumably possesses. If information can be read out of the Hawking radiation, then the black hole is not just an energy source. It is a memory device, a vast, slow-reading, cosmological scale archive of everything that ever fell into it. The civilization that built the Dyson sphere might not just be harvesting energy from their black hole. They might be reading its history, retrieving information about ancient stars, ancient planets, ancient civilizations that fell into the black hole billions of years before the current civilization even existed. The Dyson sphere, in this vision, is not just a power plant. It is a telescope pointed at the past. Now let us step back from these almost abstract heights and consider something more immediate. What would building a Dyson sphere around a black hole require of us specifically, of humanity, as we are today? What would need to happen for our civilization to move from where we are now to where we need to be? The gap is enormous, and it is worth stating clearly. Humanity is currently a type 0.7 or so civilization on the Kardashev scale. We have not yet mastered all the energy available on our own planet. We have not yet established permanent settlements beyond Earth. We have no functioning fusion power plants delivering net energy to the grid. We have not yet even sent a human being beyond the moon. The distance from where we are now to where a Dyson sphere around a black hole requires us to be is not just technological. It is also social, political, and philosophical. The transition would require millennia of sustained, coordinated progress across all domains of human knowledge and organization. It would require the resolution of existential risks that might end our civilization before we even reach Type 1 status. It would require a stability and continuity of purpose that has no precedent in human history. And yet, and this is the remarkable thing, there is nothing in the laws of physics that forbids it. The Dyson sphere around a black hole is not a magical object. It does not require unknown laws of physics. It requires known laws of physics applied at an extraordinary scale with materials and techniques we do not yet possess. Every individual element of the concept, the accretion disk, the Penrose process, the structural engineering, the energy conversion, is grounded in physics that we understand, at least qualitatively. The gaps are engineering gaps, not physics gaps. This distinction matters enormously. Throughout human history, the most transformative technologies have been ones that the physics always allowed but that we lacked the engineering sophistication to realize. The airplane did not violate any laws of physics. We simply lacked the materials and engine technology until 1903. Nuclear energy did not require new physics. It required the discovery and application of existing physics in a new engineering context. The transition to a Type 1 civilization, to a Type 2 civilization, to a civilization capable of building megastructures around black holes. None of these transitions require new physics. They require new engineering. And if the laws of physics allow it, then the question becomes not, can this be done, but when and how will it be done? The history of human technology is the history of closing the gap between what physics permits and what engineering can achieve. That gap has narrowed at every point in history. There is no reason to believe it will not continue to narrow. This might be the most important single thought you take from this exploration. The universe is not hostile to ambition. The laws of physics are not a ceiling. They are a catalog of possibilities, a complete description of what nature permits. Everything that physics permits is, in principle, achievable. And a Dyson sphere around a black hole is permitted. Let us now dive into something that recent advances in physics have brought into sharp focus. The specific types of black holes that might be most suitable for this kind of civilization-scale energy harvesting, and what the latest scientific research tells us about them. One category that has attracted increasing attention is the primordial black hole. Unlike the stellar mass black holes formed from supernova collapses, primordial black holes are hypothesized to have formed in the very early universe, in the first fractions of a second after the Big Bang, from density fluctuations in the primordial plasma. These objects, if they exist, could have a wide range of masses, from microscopic to much larger than stellar mass black holes, and their properties would differ from stellar mass black holes in several important ways. Most importantly for our purposes, primordial black holes of intermediate mass, masses that lie in the range where Hawking radiation is significant, could be genuinely extraordinary energy sources. A primordial black hole of about 10 to the 17 kilograms, roughly the mass of a small asteroid, would have a Hawking temperature of about 100,000 kelvins and a Hawking luminosity of about 100 watts. That is still modest, but a primordial black hole of 10 to the 12 kilograms would glow at billions of kelvins and radiate at truly astronomical power levels. The question of whether primordial black holes actually exist remains an active area of research. They have been proposed as candidates for dark matter, the mysterious unseen mass that makes up about 27% of the energy density of the universe and whose nature is one of the deepest open questions in physics. If primordial black holes of intermediate mass exist in significant numbers, they could explain dark matter, and they could also, potentially, be harvested by sufficiently advanced civilizations. The detection of gravitational waves from black hole mergers by the LIGO collaboration, beginning with a historic detection in September 2015, has opened a completely new window on the black hole population of the universe. Some of the mergers detected by LIGO and its partner observatory Virgo have involved black holes of masses that are slightly unusual, not impossible for stellar origin black holes, but also consistent with primordial origin. The scientific debate about whether any of the detected mergers involve primordial black holes is ongoing, with no definitive conclusion yet. But the question is being taken seriously by serious physicists. If some fraction of dark matter is composed of primordial black holes, then the universe is literally saturated with potential energy sources for advanced civilizations. Black holes wandering invisibly through every galaxy, including our own, waiting to be detected, approached, and harnessed. The irony would be exquisite. The mysterious dark matter that we have been hunting for decades, and that shapes the large-scale structure of the cosmos, is itself a potential fuel for civilizations. There is also the matter of what physicists call extremal black holes that are spinning at the maximum possible rate or have the maximum possible electric charge. These objects have special mathematical properties that make them interesting not just as energy sources but as windows into quantum gravity. An extremal Kerr black hole, spinning at its maximum possible rate, has a temperature of exactly 0, meaning it does not Hawking radiate at all. It is perfectly stable, and yet it has enormous rotational kinetic energy available for extraction via the Penrose process. An extremal Reissner-Nordstrom black hole, one with maximum electric charge, similarly has a temperature of 0 and is perfectly stable. A charged black hole could, in principle, be used as an enormous capacitor or electromagnetic energy storage system, with energy extracted by discharging it. These idealized extremal objects do not naturally occur in the universe as we currently understand it. Astrophysical black holes tend to spin relatively quickly, but not at the absolute maximum, and they tend to discharge their electric charge rapidly through interaction with surrounding plasma. But they represent the theoretical limits of what might be achievable through active management of a black hole's properties by a civilization with sufficient control over its environment. Let us pause here and consider something that is simultaneously obvious and deeply unsettling. We have now been discussing this topic for some time, exploring the physics and engineering in considerable detail, and throughout our discussion, we have been operating entirely within the framework of known or plausible physics. We have not invoked warp drives, wormholes, faster-than-light travel, or any other speculative concept that goes beyond what current physics suggests is possible. The Dyson sphere around a black hole is, in this sense, a thoroughly conservative idea by the standards of science fiction and advanced civilization speculation. And yet it is utterly, almost incomprehensibly beyond anything we currently can do. This juxtaposition, conservative by speculative standards, incomprehensible by current standards, is what makes the concept so fascinating. It exists in that precise sweet spot where science is real enough to ground the imagination and vast enough to make the imagination soar. Now let us talk about something that many discussions of Dyson spheres and black holes tend to gloss over, because it is uncomfortable: the entropy implications of building and operating such a structure, and what they tell us about the ultimate limits of any civilization's existence in this universe. The second law of thermodynamics is the most universal physical law we know. It applies everywhere, at every scale, under all conditions. It states that the entropy of a closed system never decreases. Entropy is a measure of disorder, or more precisely, of the number of possible microstates consistent with a given macrostate. When a hot object is in contact with a cold object, heat flows from hot to cold, and entropy increases. When an engine does work, it necessarily wastes some energy as heat, and entropy increases. When a star radiates light into space, entropy increases. Everything that happens in the universe increases entropy. Every process we use to extract energy and do useful work generates waste heat and increases the total entropy of the universe. A Dyson sphere around a black hole is no different. For every joule of useful work the civilization extracts from the black hole's energy, some amount of waste heat is generated and radiated away into space. The civilization is not creating energy from nothing. They are converting the black hole's ordered gravitational potential energy into useful work and waste heat, and the waste heat increases the universe's entropy. Over the very long timescales we have been discussing, trillions of years, hundreds of trillions of years, this entropy increase accumulates. Eventually, the universe reaches thermodynamic equilibrium, a state of maximum entropy where all temperature gradients have been eliminated, no more work can be extracted from any process, and the universe is dark, cold, and undifferentiated. This is the heat death of the universe, and it represents the ultimate physical limit of any civilization's existence. Even a civilization with a Dyson sphere around a black hole cannot escape this fate. They can postpone it, enormously, by tapping the long-lived energy reserves of their black hole, but they cannot prevent it. The second law of thermodynamics is a law, and laws admit of no exceptions. This might seem like a deeply depressing conclusion, and in a certain sense, it is. But there is another way to think about it. A way that Dyson himself explored in his 1979 paper and that has been elaborated by others since. If the universe is open, if it expands forever, then there may be ways to arrange the processing of information and experience that continue indefinitely even as available energy diminishes, by always operating at lower and lower temperatures and hibernating between periods of activity. The subjective experience of time would become different. Each period of wakefulness might correspond to an increasing interval of objective time, but in some sense the civilization would go on forever. This is admittedly very speculative, and it depends on the correctness of certain assumptions about the universe's ultimate fate that may not hold. The late physicist Lee Smolin and others have proposed scenarios in which the universe does not simply expand toward heat death but instead has other features. Perhaps reproduction through black holes, perhaps cycling, that could change the long-term picture. And of course, if physics contains surprises we have not yet discovered, which it almost certainly does, the long-term future of the universe may be very different from what our current theories predict. But taking current physics as our guide, the honest conclusion is this. Even a civilization with a Dyson sphere around a black hole is a temporary phenomenon on the cosmic timescale. They are buying time, an enormous, almost incomprehensible amount of time, but they are buying, not owning. Perhaps that is not a tragedy. Perhaps buying time is the most any intelligence can do. Human civilizations do not typically measure their achievement by whether they will last forever. They measure it by what they do with the time they have. By the same standard, a civilization that builds a Dyson sphere around a black hole and uses its energy to think, create, explore, and experience for trillions of years has done something extraordinary, even if it does not endure forever. There is a profound beauty in that. And in the quiet intervals between periods of activity, in the long hibernations as the universe cools, perhaps there are dreams. Perhaps intelligence, when it must wait, dreams the mathematics of its own situation into shapes we cannot imagine. Now let us consider what might be called the ecological dimension of this topic. What building a Dyson sphere around a black hole does to the broader environment. Not the environment of a planet, but the environment of the region of space surrounding the structure. The construction of a Dyson sphere around a black hole would represent one of the most dramatic alterations of a local space environment ever attempted. The sphere would change the radiation environment of the surrounding space, the gravitational influences on nearby objects, and the accretion of material into the black hole. Let us think through each of these in turn. The radiation environment. An active black hole without a Dyson sphere around it radiates energy in all directions. X-rays, gamma rays, visible light from the outer accretion disk. This radiation can influence everything in the surrounding space, potentially ionizing gas, affecting the formation of nearby stars, and even interacting with any planets that might orbit at safe distances. A Dyson sphere around the black hole would intercept this radiation completely, radically changing the radiation environment of the surrounding region. Areas that previously received intense X-ray and gamma-ray radiation from the black hole would suddenly be in shadow. If any planets or developing biospheres were in those regions, the change in their radiation environment could be dramatic. The gravitational influence. The Dyson sphere itself adds mass to the black hole system. An enormous amount of mass, as we calculated earlier. This additional mass changes the gravitational influences on any nearby objects. Stars, planets, comets, and other bodies in the vicinity of the black hole would feel a slightly different gravitational pull as the mass of the sphere accumulates. For most purposes, these changes would be negligible, but over the long timescales of galactic evolution, billions of years, even small gravitational perturbations can have dramatic effects on orbital dynamics. The accretion environment. A Dyson sphere that is actively managing the flow of material into the black hole is also changing the accretion environment. Material that would naturally fall into the black hole through gravitational attraction might be redirected or controlled by the sphere systems. The accretion disk might be maintained in a more steady state than it would be naturally, or it might be turned off entirely at certain times. This control over accretion changes the local dynamics of the gas and dust surrounding the system. These environmental changes are not trivial, and a responsible civilization, one that values not just its own survival but the health of its broader cosmic neighborhood, would need to think carefully about them. If there are other civilizations in the vicinity, those civilizations would feel the effects of the Dyson sphere's construction. If there are developing planetary systems with potential for life, those systems might be affected. The decision to build a Dyson sphere around a black hole is not just an engineering decision. It is an ecological one, on a cosmic scale. This line of thinking points toward what some thinkers call cosmic ethics or astroethics, the philosophical framework for thinking about the moral responsibilities of civilizations capable of affecting large regions of the cosmos. As we develop this framework, we are forced to confront questions that have no precedent in human moral philosophy. What obligations does a civilization have to the potential life that might exist in regions affected by its megastructures? What obligations does it have to the future civilizations that might want to use the same resources? How do we weigh the enormous benefit to one civilization against the potentially enormous costs to others? These questions are not merely academic. If humanity ever reaches the stage of building megastructures, Dyson spheres, interstellar beacons, planetary engineering projects, we will face them in a very real way. And the frameworks we develop for thinking about them, the astroethics we create, will be among the most important intellectual achievements of our civilization. Let us now turn to what may be the most speculative, but also the most emotionally resonant aspect of this entire topic. The relationship between a Dyson sphere around a black hole and the question of consciousness, meaning, and what it means to be alive. Consider what it would be like to be born on a Dyson sphere around a black hole. You would grow up in a closed environment, an engineered world, artificial in every detail but richly varied by design. You would look outward into the galaxy, watching stars slowly evolve and die over the eons. And you would know, everyone around you would know, that beneath your feet, at the center of your world, a black hole is consuming matter and radiating energy, powering every light and every breath and every thought in your civilization. The black hole would be a constant presence, not visible, not audible, not directly perceptible in any ordinary sense, but known, always known. It would be the foundation of your existence, the source of everything, a kind of God that you had built rather than imagined. Unlike the gods of human religion, which are typically imagined as beings with intentions and personalities, the black hole is a physical object governed by mathematical laws. It does not care about your civilization. It does not know you are there. It simply is what it is, doing what the laws of physics compel it to do. And yet a civilization orbiting it, enclosed around it, living from its energy, would inevitably develop a relationship with it. Not a spiritual relationship in any conventional sense, but something stranger and in some ways deeper. A relationship of total dependence that no human civilization has ever experienced. We depend on the sun, yes, but the sun is 93 million miles away, and we cannot directly interact with it, and its existence does not feel immediate to our daily lives. The inhabitants of a Dyson sphere around a black hole would feel the pull of their black hole, literally gravitationally, every moment of their existence. Their world's physical stability would be a constant testament to the engineering that holds them safe in the presence of something that could destroy them in an instant. In human psychology, total dependence on a single overwhelming source of power and danger tends to produce intense, complex relationships. Reverence, fear, gratitude, resentment. One can imagine the culture of a Dyson sphere civilization developing philosophical traditions centered around their relationship to the black hole. Traditions that grapple with the paradox of depending on something that is, in the most fundamental sense, a destroyer. Traditions that find meaning in the conversion of destruction into creation, in the act of building life and thought from the energy of something that would otherwise simply consume everything in silence. There might be rituals of the horizon, ceremonies performed at the event horizon's conceptual boundary, marking the limit beyond which nothing returns. There might be meditation practices centered on imagining the singularity, the infinite density at the center of everything, the point where the equations break down and the unknown begins. There might be art forms impossible to create in any other setting, sculptures of magnetic field lines, performances timed to the rhythm of accretion disk oscillations, music built from the gravitational wave signatures of the black hole's interactions with nearby objects. This is speculation, of course. But it is speculation grounded in a real anthropological observation. Every human culture has developed its art, mythology, and philosophy in response to its environment. The environment of a Dyson sphere around a black hole is unlike any environment human cultures have ever faced, and the culture that would emerge from it would be unlike any human culture we know. But it would still be a culture, still an expression of the fundamental human, or perhaps universal, drive to make meaning from experience. We should also consider what happens when a civilization operating a Dyson sphere around a black hole begins to think about transcendence, about moving beyond its current state into something new. For any sufficiently long-lived civilization, this is an inevitable question. The day-to-day management of a megastructure, however extraordinary, must eventually become familiar. The energy is there, the engineering works, the civilization is sustained. What next? One direction might be expansion, using the energy of the Dyson sphere to fund exploration and colonization of the surrounding galaxy. With energy sources orders of magnitude beyond anything available on a planet, interstellar spacecraft could be accelerated to significant fractions of the speed of light. At such velocities, travel to neighboring star systems takes decades to centuries rather than millennia. The civilization could spread outward, establishing colonies throughout the galaxy, each colony eventually building its own Dyson sphere around whatever energy sources are locally available. This colonization scenario has been explored extensively in the context of the Fermi paradox, the puzzle first articulated by physicist Enrico Fermi, who noted the contradiction between the apparent probability that intelligent life should be common in the universe and the complete absence of any evidence for it. If intelligent civilizations are common, and if they eventually build megastructures and develop interstellar travel, the galaxy should have been colonized many times over by now. We see no evidence of such colonization. Why? Possible answers range from the sobering, most civilizations die before reaching the megastructure stage, due to self-destruction or other existential risks, to the puzzling, civilizations that reach the megastructure stage choose not to colonize, for reasons we do not understand, to the intriguing, the colonization has happened, but we have not recognized it. Perhaps the dark matter is primordial black holes being actively managed by ancient civilizations, or perhaps certain anomalous astronomical objects are the remnants of civilizational activities long since concluded. The Fermi paradox, combined with the concept of Dyson spheres around black holes, creates a deep and deeply uncomfortable mystery. If the physics allows civilizations to survive for cosmological timescales by building megastructures around black holes, and if the universe is old enough and large enough for many such civilizations to have arisen and developed, then the universe should be full of them. And yet we see silence. Why the silence? This is a question that has haunted astronomers and philosophers since Fermi first posed it in 1950, and it remains one of the most profound open questions in all of science. Every answer leads to more questions. Every theory of the Fermi paradox has implications for our own future. If civilizations typically destroy themselves before reaching the megastructure stage, what kills them? Is it nuclear war? Environmental collapse? The development of artificial intelligence that turns on its creators? A kind of civilizational ennui that saps the collective will to continue? Each of these possibilities is both a warning and a challenge. The concept of the Great Filter, introduced by economist Robin Hanson in 1998, argues that there must be some extremely difficult or rare step in the development of a civilization from simple life to an interstellar presence that most potential civilizations fail to achieve. This step, whatever it is, filters out almost all civilizations before they can expand to the point of being detectable from Earth. If the Great Filter is behind us, if humanity has already passed the hardest step, then we may be very rare and our prospects for continuing to advance are relatively good. If the Great Filter is ahead of us, if the hardest step is still to come, then the silence of the cosmos is a dire warning about our own future. A Dyson sphere around a black hole represents, in this framework, the other side of the Great Filter, the thing that a civilization achieves if it successfully navigates all the filters. It is the emblem of ultimate survival. And the silence of the cosmos on that frequency might mean that the filters are indeed brutal, that it is extraordinarily rare for any civilization to reach the point of building one. Or it might mean something stranger and harder to contemplate, that civilizations which do reach this stage evolve so thoroughly, become so different from what they were, that their presence is invisible to our current instruments and frameworks. That a civilization living on a Dyson sphere around a black hole, thinking thoughts on timescales of centuries, communicating through means we have not yet imagined, has become effectively undetectable by a young species still pointing radio telescopes at the sky. Perhaps they are all around us, invisible in their maturity, as invisible as the dark matter they might have made, as silent as the void that surrounds us. And the silence is not emptiness, but the quiet of something so far beyond us that we cannot yet hear it. Ask yourself this: if you discovered tomorrow that a structure, vast, ancient, built of some material unknown to science, surrounded a black hole 20 light-years from Earth, what would that do to everything you believe about our place in the universe? What would it do to human civilization to know that we are not the first? That someone has already been where we are going? That the universe is not waiting for us but was already colonized before our ancestors learned to build fire? Now let us talk about something that is quite recent in the scientific literature and that adds a remarkable dimension to everything we have been discussing. The role of quantum gravity and quantum information theory in understanding what a Dyson sphere around a black hole might achieve. Quantum gravity is the sought-after theory that unifies quantum mechanics and general relativity, the two pillars of modern physics that, as we discussed in the context of the information paradox, are known to be incompatible in their current forms. The development of a complete quantum gravity theory is widely regarded as the greatest unsolved problem in theoretical physics. Candidates include string theory, loop quantum gravity, and several other approaches, but none has yet been experimentally confirmed or fully developed mathematically. What quantum gravity might reveal about black holes could be revolutionary. One of the most startling possibilities, explored in the context of loop quantum gravity by Abhay Ushtekar and others, is that the singularity at the center of a black hole is not real. In loop quantum gravity, spacetime has a granular structure at the Planck scale, the incredibly small scale at which quantum gravitational effects become important, and this granularity prevents the formation of true singularities. Instead of collapsing to a point of infinite density, the collapsing material bounces back at Planck density, potentially exploding outward again in what some researchers call a Planck star or bouncing black hole. In this scenario, the interior of a black hole is not a one-way trap, but a kind of extreme environment that eventually re-expands into our universe or into a new region of spacetime. If this is correct, and it remains a speculative but mathematically consistent proposal, then a black hole is not just a consumer but potentially a creator. Material that falls in may eventually come back out, transformed by the extreme physics of the bounce. A civilization with a Dyson sphere around a black hole might eventually witness this bounce, or might even be able to interact with it, extracting additional energy and information from the process. This idea connects to another speculative but serious proposal: Lee Smolin's cosmological natural selection hypothesis, sometimes called cosmic evolution or fecund universes. Smolin proposed in the 1990s that black holes give birth to new universes when they form, that the bounce at the Planck scale creates a new region of spacetime with slightly different physical constants, analogous to biological reproduction with slight mutations. In this framework, the universe we live in is descended from earlier universes that produced large numbers of black holes, and the physical constants of our universe are tuned to produce many black holes, because universes that produce many black holes produce many offspring, and so their physical parameters dominate over cosmological timescales. This is a bold and genuinely fascinating hypothesis, though it remains unproven and not widely accepted in the mainstream of theoretical physics. But it raises a remarkable implication. If black holes give birth to new universes, then a civilization that feeds and maintains a black hole, a civilization that maximizes its black hole's production of new universes, might be an engine of cosmic creation. Not just using the universe, but extending it. Not just surviving in the cosmos, but contributing to the cosmos in the most fundamental sense imaginable. This is perhaps the most extraordinary idea we have encountered yet, and we should hold it gently, as a speculation rather than a fact. But it is a speculation that physicists have taken seriously, that has been published in peer-reviewed journals, and that illuminates a possibility so grand that it defies ordinary human language. What would it mean for a civilization to know that their engineering was creating universes? What ethical frameworks, what philosophical traditions, what art and meaning would emerge from that knowledge? A civilization that builds a Dyson sphere around a black hole and feeds it, knowing that in doing so they are potentially birthing new cosmos after cosmos, would face philosophical questions of a depth and strangeness that make even the hardest human existential questions look modest. Now let us visit one more extraordinary angle of this topic: the possibility of using the Dyson sphere and its black hole as a weapon, not in the sense of firing it at enemies, though that too has been discussed in various speculative contexts, but in the more subtle and perhaps more genuinely alarming sense of using it for competitive advantage in a universe that might contain other civilizations. The concept of dark forest theory, popularized by Chinese science fiction author Liu Cixin in his trilogy beginning with The Three-Body Problem, proposes that the silence of the cosmos is not benign but strategic. In Liu's formulation, every civilization in the universe knows that the universe's resources are finite and that any unknown civilization it encounters might be a threat. The rational strategy, therefore, is to destroy any civilization you become aware of before it becomes powerful enough to threaten you, to maintain the silence by eliminating all sources of signals. The universe is silent not because civilizations are rare, but because they are hiding. In this framework, a civilization that builds a Dyson sphere around a black hole has made itself both enormously powerful and enormously visible. The waste heat of such a structure, the infrared glow of a captured and recycled energy source, cannot be hidden by any known means of physics. It is a beacon announcing to the entire galaxy, "Here I am. I am powerful. Come and see me." If dark forest theory is correct, that beacon is also a target. A civilization that sees the infrared glow of a megastructure knows where you are. And if they calculate that you are a potential future threat, or if their strategy demands the elimination of all technological civilizations regardless of immediate threat, then your beacon is also your death sentence. Liu Cixin did not invent this concern. It has been discussed by Sirius SETI researchers as a reason to be cautious about active messaging, transmitting signals into space that might alert other civilizations to our presence. The messaging extraterrestrial intelligence, or METI, debate is a real and ongoing scientific and ethical discussion, with some researchers, including Stephen Hawking, having argued that broadcasting our presence could be dangerous. A Dyson sphere around a black hole is not a radio signal. It is something more permanent, more massive, and more unavoidable. It is a monument. And like all monuments, it speaks to whoever is listening. Whether dark forest theory is correct is unknown. It represents one possible resolution of the Fermi paradox, but it is not the only one and not necessarily the most likely one. Many researchers consider it too pessimistic about the nature of intelligence and the incentives of advanced civilizations. Biologist E.O. Wilson and others have argued that cooperation, rather than competition, is actually the more likely dominant strategy for civilizations advanced enough to build megastructures, because the resources available in the universe are so vast that conflict over them is irrational. But the dark forest scenario is a genuine possibility that a civilization contemplating a Dyson sphere around a black hole would need to take seriously. The structure's visibility is unavoidable. The question is whether that visibility is a risk, an invitation, or simply an inevitable consequence of being alive in the universe. Let us now consider what the discovery of a Dyson sphere around a black hole would mean for humanity right now, in our current moment, before we have built anything of the kind ourselves. The discovery of such a structure, confirmed beyond any reasonable doubt to be artificial, to be engineered, to be the work of another intelligence, would be, without hyperbole, the most significant event in human history. Nothing in our experience, nothing in our philosophy, nothing in our religion or science or art has prepared us for that moment. The discovery of any extraterrestrial life, even microbial life, would be transformative. But the discovery of a civilization that has engineered a structure encompassing a black hole would be the discovery not just of life but of transcendent technological capability. A capability so far beyond our own that it would recategorize us from the most advanced intelligence we know of to a young and primitive newcomer in a universe already occupied by gods. How would humanity respond? This is not just a thought experiment. Governments, military organizations, and scientific bodies have actual protocols for responding to the detection of extraterrestrial intelligence. Protocols developed by bodies like the SETI Institute and the International Academy of Astronautics. These protocols are generally sensible. Verify the signal through independent observations. Consult internationally before responding. Avoid precipitous broadcasting. But no protocol can really prepare us for the psychological shock of confirmation. The religious implications alone would be staggering. Every major world religion has developed its theology in the context of a universe that, as far as we knew, contained only us. The discovery of another intelligence, and especially one of vastly superior capability, would force every religious tradition to grapple with what it means for their narratives of human uniqueness, divine creation, and the purpose of existence. Some traditions might adapt readily. Many theologians have already explored scenarios of extraterrestrial intelligence and found them compatible with their beliefs. Others might find the challenge more existential. The scientific implications would be both humbling and inspiring. Every physicist, every engineer, every material scientist would want to know, what are they built from? How do they do it? What can we learn from the mere fact of their existence? The discovery of another civilization would immediately tell us that the Great Filter, whatever it is not necessarily fatal. That at least one other species has navigated all the challenges and emerged on the other side, alive and building. That knowledge alone could transform our assessment of our own prospects. Economically, politically, and strategically, the implications would be disruptive on a scale that defies analysis. Every geopolitical calculation, every economic assumption, every military strategy would need to be rewritten in the context of a universe containing at least one vastly more advanced civilization. The response of different nations and power blocks to that knowledge would vary enormously, and the potential for conflict over how to respond, whether to attempt communication, whether to hide, whether to accelerate our own technological development, would be enormous. But perhaps most importantly, the discovery would do something to the human spirit that nothing else has ever quite managed. It would give us a destination. Not a destination in space. The black hole might be thousands of light years away, but a destination in ambition. A proof of possibility. A demonstration that the road we are on, the road of science and engineering and increasing mastery of nature, leads somewhere. That it is not a road to nowhere. That might matter more than anything else. Now let us talk about the cutting-edge research that is happening right now, in our current moment, in the early 21st century, that is laying the foundations for everything we have discussed. The Event Horizon Telescope, the planet-scale array of radio observatories that produced the first image of a black hole shadow in 2019, continues to improve its resolution and sensitivity. The 2019 image of M87 star and the subsequent 2022 image of Sagittarius A star at the center of the Milky Way are just the beginning. Next-generation versions of the Event Horizon Telescope, potentially including space-based components, could eventually resolve structure inside black hole accretion disks at the level of Schwarzschild radii, close enough to test theories of the innermost stable circular orbit, the photon sphere, and even hints of Penrose process-relevant dynamics. The LIGO and Virgo gravitational wave detectors have opened a completely new observational window on the universe since 2015. They have detected dozens of black hole mergers, each providing new information about the masses, spins, and populations of black holes throughout the universe. The third-generation gravitational wave detector Einstein telescope, proposed for construction in Europe, would be sensitive enough to detect black hole mergers throughout the entire observable universe, providing a complete census of merging black holes and dramatically improving our understanding of the black hole population and its properties. The James Webb Space Telescope, launched in December 2021, is already transforming our understanding of the early universe. Its infrared sensitivity allows it to observe the first galaxies to form after the Big Bang, and it is revealing black holes of extraordinary mass existing surprisingly early in cosmic history. Black holes that should not have had enough time to grow to their observed sizes through conventional accretion. This problem of early massive black holes is one of the most active research areas in current astrophysics, and its resolution may require modifications to our understanding of how black holes grow, modifications that could be relevant to the engineering of a Dyson sphere around a black hole. In theoretical physics, the last decade has seen remarkable progress on the information paradox front. The island formula results we discussed earlier have been replicated and extended by multiple research groups, strengthening the case that information is preserved in black hole evaporation. Connections between the AD/CFT correspondence and quantum information theory, particularly the concept of quantum error correction, have provided new tools for thinking about how information is encoded on and near black hole horizons. These developments do not immediately translate into engineering blueprints, but they deepen our understanding of the fundamental physics of black holes in ways that will eventually matter for any civilization that tries to interact with one seriously. In materials science, progress continues on multiple fronts relevant to megastructure engineering. Graphene, the single atom-thick form of carbon discovered in 2004, has extraordinary mechanical properties. It is 200 times stronger than steel by weight, nearly transparent, and an excellent conductor of heat and electricity. More complex carbon allotropes and two-dimensional materials continue to be discovered and characterized. The development of bulk nanostructured materials, materials with design properties at the nanoscale, is advancing rapidly. None of these materials are close to what a Dyson sphere around a black hole would require, but they represent genuine progress along the technological trajectory that would eventually produce the necessary materials. In computation and artificial intelligence, the acceleration of progress is visible to everyone. Artificial intelligence systems are increasingly capable of autonomous reasoning, scientific discovery, and engineering design. Future AI systems, operating at scales we cannot currently predict, might serve as the primary designers and builders of megastructures, creating engineering solutions that human engineers could not find and supervising construction processes that no human could directly oversee. In propulsion, research continues on advanced concepts like nuclear pulse propulsion, using small nuclear explosions for thrust, laser sail propulsion, and antimatter propulsion. These concepts are not yet engineering realities, but they represent paths toward the interstellar travel capability that would be needed to reach a black hole in another star system. The black hole at the center of the Milky Way, Sagittarius A star, is about 26,000 light-years away, not accessible with any near-term propulsion system. But stellar mass black holes are scattered throughout the galaxy at much closer distances. The nearest known black hole candidate, Gaia BH1, is about 1,500 light-years from Earth, and recently observed systems suggest there may be black holes much closer than that. All of this research is connected. All of it is building toward a future that, from the perspective of our current moment, looks as remote and fantastical as the future of aircraft looked to a medieval peasant. And yet we are not making those preparations deliberately, with a Dyson sphere in mind. We are making them out of scientific curiosity, out of technological ambition, out of the simple human drive to know and to build. The Dyson sphere is what waits at the end of that drive, a destination that no individual scientist or engineer is aiming for, but that the collective trajectory of human knowledge is inexorably approaching. It is worth pausing here to appreciate something about the nature of scientific progress that the Dyson sphere concept illuminates particularly clearly. The history of science and technology is full of ideas that were considered impossibly ambitious at the time of their proposal, but that eventually became real. Heavier-than-air flight was widely considered impossible in the decades before the Wright brothers. Splitting the atom was a theoretical curiosity of academic physics before it became the defining technological achievement of the 20th century. Sequencing the human genome seemed impossibly expensive and slow when the Human Genome Project began, and yet it was completed, and today entire genomes are sequenced in hours. The pattern is consistent. Extraordinary things that physics permits eventually become ordinary things that engineering delivers. The gap between physics permits it and engineering delivers it has been closing throughout human history. The question is not whether it will close in the case of the Dyson sphere around a black hole. The question is when and what the civilization will look like when it does. Now let us explore, in more concrete terms, the specific sequence of technological and social developments that might bridge the gap between our current civilization and one capable of building a Dyson sphere around a black hole. This is necessarily speculative, but it is informed speculation, guided by the logic of technological development and by the specific requirements we have identified. The first stage might be what we could call the solar system stage. This is the period in which a civilization like humanity achieves complete mastery of its own solar system, mining asteroids and comets for raw materials, establishing permanent settlements on multiple worlds, deploying large-scale solar power satellites in space, and developing propulsion systems capable of reaching any point in the solar system within weeks or months. In this stage, the civilization's total energy use reaches and exceeds the Kardashev Type 1 level. This stage might take humanity 1 to 2 centuries at current rates of technological development. The second stage might be the nearby interstellar stage. The civilization develops propulsion systems capable of reaching nearby star systems within decades and establishes its first interstellar colonies. The resources of multiple stellar systems become available. The civilization's energy use begins to approach Kardashev Type 2. This stage might require advances in propulsion, nuclear pulse, laser sail, or something currently unimagined, and would likely require the development of advanced AI to manage the complexities of an interstellar civilization. This stage might take 1 to 10,000 years from the current moment. The third stage might be the megastructure stage. The civilization has access to the resources of multiple stellar systems, has the materials technology to build structures of planetary mass, and has identified and studied black holes in its neighborhood. The first Dyson swarms, not full spheres, but partial collections of energy-collecting satellites, might be built around the most accessible black holes. This stage might span thousands to millions of years. The fourth stage might be the full Dyson sphere stage, a complete enclosure of a black hole, with active management of the accretion disk and optimization of energy extraction via the Penrose process. This stage represents full Kardashev Type 2 to Type 3 energy access, depending on the black hole's properties. The civilization at this stage is truly cosmic. Its ambitions, its culture, its mode of existence bear no recognizable resemblance to what we are today, though they are descended from us. In materials science, progress continues on multiple fronts relevant to megastructure engineering. Graphene, the single atom-thick form of carbon discovered in 2004, has extraordinary mechanical properties. It is 200 times stronger than steel by weight, nearly transparent, and an excellent conductor of heat and electricity. More complex carbon allotropes and two-dimensional materials continue to be discovered and characterized. The development of bulk nanostructured materials with design properties at the nanoscale, is advancing rapidly. None of these materials are close to what a Dyson sphere around a black hole would require, but they represent genuine progress along the technological trajectory that would eventually produce the necessary materials. In computation and artificial intelligence, the acceleration of progress is visible to everyone. Artificial intelligence systems are increasingly capable of autonomous reasoning, scientific discovery, and engineering design. Future AI systems, operating at scales we cannot currently predict, might serve as the primary designers and builders of megastructures, creating engineering solutions that human engineers could not find and supervising construction processes that no human could directly oversee. In propulsion, research continues on advanced concepts like nuclear pulse propulsion, using small nuclear explosions for thrust, laser sail propulsion, and antimatter propulsion. These concepts are not yet engineering realities, but they represent paths toward the interstellar travel capability that would be needed to reach a black hole in another star system. The black hole at the center of the Milky Way, Sagittarius A star, is about 26,000 light-years away, not accessible with any near-term propulsion system. But stellar mass black holes are scattered throughout the galaxy at much closer distances. The nearest known black hole candidate, Gaia BH1, is about 1,500 light-years from Earth, and recently observed systems suggest there may be black holes much closer than that. All of this research is connected. All of it is building toward a future that, from the perspective of our current moment, looks as remote and fantastical as the future of aircraft looked to a medieval peasant. And yet we are not making those preparations deliberately, with a Dyson sphere in mind. We are making them out of scientific curiosity, out of technological ambition, out of the simple human drive to know and to build. The Dyson sphere is what waits at the end of that drive, a destination that no individual scientist or engineer is aiming for, but that the collective trajectory of human knowledge is inexorably approaching. It is worth pausing here to appreciate something about the nature of scientific progress that the Dyson sphere concept illuminates particularly clearly. The history of science and technology is full of ideas that were considered impossibly ambitious at the time of their proposal, but that eventually became real. Heavier-than-air flight was widely considered impossible in the decades before the Wright brothers. Splitting the atom was a theoretical curiosity of academic physics before it became the defining technological achievement of the 20th century. Sequencing the human genome seemed impossibly expensive and slow when the Human Genome Project began, and yet it was completed, and today entire genomes are sequenced in hours. The pattern is consistent. Extraordinary things that physics permits eventually become ordinary things that engineering delivers. The gap between physics permits it and engineering delivers it has been closing throughout human history. The question is not whether it will close in the case of the Dyson sphere around a black hole. The question is when and what the civilization will look like when it does. Now let us explore in more concrete terms the specific sequence of technological and social developments that might bridge the gap between our current civilization and one capable of building a Dyson sphere around a black hole. This is necessarily speculative, but it is informed speculation, guided by the logic of technological development and by the specific requirements we have identified. The first stage might be what we could call the solar system stage. This is the period in which a civilization like humanity achieves complete mastery of its own solar system, mining asteroids and comets for raw materials, establishing permanent settlements on multiple worlds, deploying large-scale solar power satellites in space, and developing propulsion systems capable of reaching any point in the solar system within weeks or months. In this stage, the civilization's total energy use reaches and exceeds the Kardashev Type 1 level. This stage might take humanity 1 to 2 centuries at current rates of technological development. The second stage might be the nearby interstellar stage. The civilization develops propulsion systems capable of reaching nearby star systems within decades, and establishes its first interstellar colonies. The resources of multiple stellar systems become available. The civilization's energy use begins to approach Kardashev Type 2. This stage might require advances in propulsion, nuclear pulse, laser sail, or something currently unimagined, and would likely require the development of advanced AI to manage the complexities of an interstellar civilization. This stage might take 1 to 10,000 years from the current moment. The third stage might be the megastructure stage. The civilization has access to the resources of multiple stellar systems, has the materials technology to build structures of planetary mass, and has identified and studied black holes in its neighborhood. The first Dyson swarms, not full spheres, but partial collections of energy-collecting satellites, might be built around the most accessible black holes. This stage might span thousands to millions of years. The fourth stage might be the full Dyson sphere stage, a complete enclosure of a black hole, with active management of the accretion disk and optimization of energy extraction via the Penrose process. This stage represents full Kardashev Type 2 to Type 3 energy access, depending on the black hole's properties. The civilization at this stage is truly cosmic. Its ambitions, its culture, its mode of existence bear no recognizable resemblance to what we are today, though they are descended from us. The current age of the universe is about 13.8 billion years. In the cosmological future, the universe's evolution will pass through several distinct phases. We are currently in the stelliferous era, the era of stars, which will last for roughly 100 trillion years, the time it takes for the smallest, dimmest red dwarf stars to exhaust their hydrogen fuel. During this era, new stars will continue to form and die, and the universe will remain relatively bright and energetic. After the stelliferous era ends, the universe enters the degenerate era. New star formation ceases. There is no more raw material falling together to ignite new fusion. The galaxy is populated by stellar remnants, white dwarfs, neutron stars, and black holes. The white dwarfs cool and dim over time, eventually becoming black dwarfs, cold, dark cinders of carbon and oxygen. The neutron stars cool and darken. Only the black holes remain energetically active, still radiating Hawking radiation, still accumulating whatever small amounts of material drift near them. During the degenerate era, which lasts from about 10 to the 14 to about 10 to the 40 years, a civilization on a Dyson sphere around a black hole is one of the last beings in the universe with access to a significant energy source. All the stars are dead. The galaxy is dark. But their black hole is still there, still radiating, slowly, yes, but steadily. They are effectively the last light in a darkening universe. After the degenerate era comes the black hole era, the era dominated by black holes. During this period, which runs from about 10 to the 40 to about 10 to the 100 years, black holes dominate the mass energy content of the universe. They evaporate through Hawking radiation on these enormous timescales, larger black holes evaporating more slowly than smaller ones. A stellar mass black hole evaporates in about 10 to the 67 years, a timescale that makes the current age of the universe look like a nanosecond. A black hole of 1,000,000 solar masses evaporates in about 10 to the 83 years. A supermassive black hole of 1,000,000,000 solar masses evaporates in about 10 to the 96 years. These numbers are so large that they essentially define the boundary of imaginable time. During the black hole era, a civilization that has built a Dyson sphere around a sufficiently massive black hole has access to Hawking radiation as its primary energy source. As we noted, the Hawking radiation is extremely cold, nanokelvins for stellar mass black holes, but it is energy. A sufficiently organized civilization could, in principle, use this cold thermal energy to do useful work against the even colder background of cosmic expansion. As the black hole evaporates, its temperature rises and its luminosity increases, eventually culminating in a dramatic burst of radiation as the black hole approaches its final moments. Those final moments, the last seconds of a black hole's evaporation, when the temperature reaches extreme values and the luminosity spikes, might actually be the most energetically productive moments of the black hole's entire existence in terms of power output per unit time. A civilization that has lived alongside their black hole for its entire lifetime. A civilization that has been there from the construction of the Dyson sphere to this final moment, would witness something no other being in the universe has ever seen: the total evaporation of a black hole.